Again, in the theme of building capability, it's my great pleasure to introduce Han-Li Liu, who's a senior scientist in HAO and has been one of the key developers, proponents, and pushers. You use that in probably the most colloquial sense, pushers of the WACOM-X project. WACOM-X is a real strategic push for us moving forward, and I'll leave up to Han-Li to give you the background and future paths, hopefully. Thanks.
Thank you, Scott, and thanks for the opportunity to speak here. Also, I think it's being speaking here implied that I'm still belonging to the future generation, which is, very, I'm very grateful for that. So a bit history on the development of WACOM-X. If we think back, I think genesis goes back to time GCM, the thermosphere, ionosphere, mesosphere, and electrodynamic general circulation model, which was developed by Ray Robo and his colleagues since the 70s, so a long history and heritage there. And in the development, especially in the later stage of development, there's increasing appreciation for the lower atmosphere forcing. So these are the some important aspect of in the model that consider the lower atmosphere. Well, one is the tidal forcing from the GSWM, and though it's more like the climatological forcing from the tides. And then very close to my heart is the gravity wave forcing, and of course in the most of GCM models, they are parameterized, and this is my postdoc project and how I get involved in the large-scale modeling. And later, Ray has developed boundary forcing from NCEP or ECMWF, in his words, to shake the lower boundary harder to see what kind of variability we'll get in the upper atmosphere. And then to make things more self-consistent, I think in the late 90s, Ray introduced this really a whole atmosphere model. It's a coupled time GCM with a CCM3, a lower atmosphere climate model. And I said that gravity wave forcing is close to my heart. This is kind of my first project here. This is from the parameterization we developed, the zonal mean gravity wave forcing as a function of latitude and height. And you can see that the eastward forcing and the westward forcing, they were able to close the jet. So this is the zonal mean zonal wind in the atmosphere from 30 to 100 kilometers from time GCM. So you can see that the winter jet was closed and reversed, and so it's a summer jet. So we're introduced the forcing, and it seems it's doing its work. And then, and actually, you can see it's actually a run made by Ray, and for a whole year. So he started from January and go all the year. And even today, running time GCM through a year is still a very significant effort. So this is zonal mean, or not zonal mean, it's the temperature at mid-latitude in the northern hemisphere from that whole year run, and January through December. And from the ozone heating, you can see that the model generates a pretty good warming, or the right climatology, the warm summer stratosphere. And in the winter, it seems we have a very cold summer, cold summer mesosphere, which is driven by the gravity wave, secondary the mesosphere circulation driven by the gravity wave. And that's all good. And then, as I mentioned earlier, Ray decided to shake it harder, and he introduced the NCEP reanalysis, daily output from the reanalysis. And then he ran the model again. And you can see that even though the general climatology is very similar, but you see much more variability. And we can pick out, for example, during the winter time, a few very strong planetary wave cases where generate stratosphere warming, and the impact goes all the way to the lower thermosphere. And in the summertime, there's less planetary wave forcing, so the stratosphere is generally quiet, but you can see still a lot of variability higher up. And part of that is because of the traveling planetary wave, and some of that is due to geomagnetic forcing. So, and then a whole atmosphere model at that time is the interacting time GCM, CCM3. And using the model, we can do a lot of fun things. One thing we did was we can observe the self-generation of stratosphere, very strong stratosphere warming case. Here is the temperature, the color contour here is the temperature, zonal mean temperature as a function of latitude and height. And you can see a very strong warming, but accompanying that, there's a very strong mesosphere cooling and secondary warming higher up in the thermosphere. And actually, also you can see temperature changes at lower latitude. And with that, you see the planetary wave forcing causes the reversal of the jet, westward reversal of the jet, and the gravity wave forcing causing the other change in the other direction in the mesosphere. So with that model, we can kind of elucidate all those processes. And from the exercise, we can see a very clear coupling throughout the whole atmosphere. So then there's this a report in 1999, the UCAR quarterly report, and the three visionaries who really started this. And some quotes, I should zoom in the quotes, but basically at that time, it's a yet named whole atmosphere model, or yet named model. So WACOM hasn't got its name yet at that time. But basically, Ray said here, we have never been able to really resolve the variability in the lower thermosphere and ionosphere. So one motivation is to do this right, we have to have one model that does it all. Basically, he wants to consider everything in the atmosphere and study the whole atmosphere coupling. And also he mentioned Walt Roberts' dream to kind of study the solar impact on the weather and climate. So basically, that's the science objective of WACOM. Study the solar impact on the whole Earth system, and also try to understand the various processes that was controlling the coupling process, and also study the implications for the coupling for climate, for the downward coupling, and also for the to the space environment for the upward coupling. And this is the current where we stand in the whole atmosphere model, the status. And it's built on this framework of the NCAR CESM, Community Earth System Modeling framework. And atmosphere is one of the, I think, 8 components. And there, of course, there are ocean, land, and sea ice, all those different components. And atmosphere, of course, is a key component there. And the usual, the normal run for CSM runs, only the lower atmosphere version is used, the CAM, the Community Atmosphere Model. And WACOM is built on CAM by including all this physics, physical and chemical processes. And for DICOR, for WACOM, we usually use the finite volume DICOR, and we're experimenting with the new spectral element core. And chemistry, there's a full package of Mozart chemistry, including ion chemistry, and it's fully interactive with the dynamics. And the physics, we've considered full spectrum from EUV to IR, and their photolysis and the radio transfer, and various parameterizations capture the middle and lower atmosphere processes. And thermosphere factors are considered, and this column is mainly the ionosphere component. And most of this are now implemented, except this one is still under development, and are being tested too. So this is the usual model configurations, and as I mentioned earlier, we're using the new DICOR to try some really high mesoscale resolving capability of the model. So these are the kind of key capabilities. On the first order, we need to get the climatology and the structures right, from the ground to the exobase. So that includes the compositional, thermal, and wind structures. And next order, of course, we want to study the variability from lower atmosphere all the way to the upper atmosphere, and on different scales, time scales and spatial scales. And with the new capability, maybe we can go down all the way to the mesoscales. And also the other important capability is trying to use the model to do research hindcast or forecast. And for that, we need to either specify the climatology or meteorology or simulating data from the lower atmosphere all the way to the upper atmosphere. And this is very important for supporting the upcoming missions, ICON, Gold, and Cosmic 2. And just to show you that the compositional, thermal, and wind structures, this is a major species in the model. It all resolved by itself, the 002N2, from the ground to the upper thermosphere. And this is the global average, and this compares very well with our climatology and race global mean model. And this is the main ion and ion species and electron. And they're pretty good up to about the F peak. And higher, we're doing better now with the implementation of the new ionosphere component by considering the bipolar diffusion and the O-polar transport. So this has improved since we published paper in 2010. And this is the wind. You can see the troposphere wind, the westerly jet, westerly wind are resolved pretty well, and then the polar winter stratosphere jet, and easterly in the summer hemisphere, and the reversal from gravity waves, and the thermosphere wind with some superrotation. And then the temperature also, general structure is very good compared with climatology. It's a little bit cool higher up because at that time we haven't considered all the energetics in the model yet, and we're improving on that now. On the variability, this is from a 20-year run of a WACOM-X, and we're trying to study the whole atmosphere kind of teleconnection pattern by looking at the correlations. So here we're trying to correlate all the temperature anomaly in the whole region from the ground to the upper thermosphere with the temperature anomaly in the polar stratosphere, winter polar stratosphere. The reason is because that's an area that's often very strongly disturbed by planetary waves. And you can see that with the, say, warming or cooling here, there's a very strong positive correlation even extending up to the upper thermosphere. And this is the shade for statistical significance. So there's quite a significant correlation going all the way up to the upper thermosphere, and similar pattern in the southern winter time. And actually, there's a recent paper by Yamazaki, who was a graduate student and also postdoc here, working with Art Richmond. It's now at UK. They published a result recently from satellite drag measurement, and these are densities. I think, yes, densities, thermosphere density averaged over the whole globe because it's extracted from the integrated satellite drag, and at a couple of different height from 270 kilometer to 575, and they correlate or try to look for relation with the stratosphere temperature. So this is a warming time period. Let's see why it looks like a cooling here. Maybe it's a mesosphere cooling. Okay. Anyway, so what they pointed out in the paper is that during the disturbed times, you usually see a decrease in the density, thermosphere density, and which is kind of consistent with the temperature increase if we consider, because this is on the pressure grid. So with the temperature decrease, you usually get density decrease. So these are more or less consistent. So we're very encouraged by those observation results. Of course, we haven't looked at in too much detail on the mechanism of this change. So that's something we need to study further. And then on shorter term variability, this is again from that 20-year run, but here we only look at the tidal amplitude from the simulation. And we can see that there are very large day-to-day variability and persisting throughout the simulation. So it's a very ubiquitous feature that it's a very, the tides can vary very strongly from day to day. And the implication for that, we studied that in using the WACOM model, but use that to drive the ionosphere electrodynamics in time GCM, because at that time we still haven't had the ionosphere implemented in WACOM-X. So this is what we got from 2 months of simulation, January and February. And using those highly variable wind fields, including the tidal variability, to drive the dynamo we see that the vertical drift and the zonal drift all show very large variability at low latitude. This shaded or the gray lines are the daily values from that 2-month run, and the black line is the average. So there's a large scattering and indicating the large day-to-day variability that compare quite well with observations. And also the standard deviation compares pretty well. So it seems the weather in the ionosphere has a lot to do with the weather from lower down. Once we introduce those large variabilities, it seems that we do get very large weather perturbations higher up. So then this is, and then there's some case studies. So this is work done by Nick Patella, who was a postdoc working at HAO, now at Cosmic Division. And so he decided to look at the use of WACOM, which is constrained by some lower atmosphere of climatology, or not climatology, reanalysis, and then use that same setup to drive time GCM. Because again, we didn't have that capability yet. So, and then he looked at the vertical drift over 2 months in January, February of 2009, where there's a very strong stratosphere warming case. And this is a vertical drift as a function of time, day of the year, and then local time. So he was able to get quite large day-to-day variability in the vertical drift, and also not only in the magnitude change, but also the phase of the local time phase of the vertical drift, and which compares very well with the observation. This is an observation, I think, at the Hikamarka. And also he added the lunar tides, demonstrated the lunar tides is very important, plays a very important role in the variability. This is without the lunar tides. And as I mentioned again and again, that we were missing some important capabilities in the ionosphere. And so, of course, we need to build that in. And then recently, sorry, there's a cut out a little bit. And so recently we have implemented the electrodynamics and also the O+ transport in the model for, to better represent the ionosphere. So here is what we got for the vertical drift and zonal drift. And the climatology in general looks pretty good. And during the daytime, you have upward drift, and you have a pre-reversal enhancement, and around dusk, and then downward at night. And zonal drift, westward drift during the day, eastward drift in the night, with very large amplitude. Actually, that's doing better than what we saw in time GCM. And then this is the total electron density at near F2 peak. So you can see the EIA anomaly, the equatorial ionosphere anomaly is well reproduced because we're doing the vertical drift right. So that capability is now in the model and it's being tested and verified. So another thing is we want to, as mentioned earlier, it's important to study the predictability of whole atmosphere models. So again, Nick did the study. He put together 4 whole atmosphere models: Gaia, Harmonia, Japanese German model, and NOAA WAM, and also the WACOM-X. And this is again for the 2009 January-February time period. And what's done in the model is the lower atmosphere up to middle stratosphere, they are either constrained by reanalysis or they are data simulated. So the lower atmosphere is almost identical up to the stratosphere. But you can see that higher up in the mesosphere and the lower thermosphere, the wind diverge quite significantly from model to model. And when he analyzed the results, he thinks that concluded that the main cause of those divergence or the difference is coming from different gravity waves from different models. So the gravity wave is a major source of model bias and deviation in the upper atmosphere. So then what he did is try to use data simulation to constrain this, and he make some further model runs. Actually, he developed this WACOM DART which stands for Data Simulation Research Testbed. It's in collaboration with Jeff Anderson and Kevin Rader in March. And he built this system, and he was able to demonstrate once you assimilate lower atmosphere and upper atmosphere data from SABRE and MLS, you can do a much better job. One distinct feature here is the elevated stratopause following stratosphere warming, and it doesn't show the very large descending rate, unrealistic large descending rate that is in other models, or if you don't assimilate the data. So only 3 minutes, so I will just show you some highlights from a recent study from the Mesoscale Resolving WACOM. And so here we're looking at results of the vertical wind at different levels from the tropopause all the way to the thermosphere. And you can see that in response to this very large, deep convection, we have a lot of gravity waves that propagate up, and they become very significant when they go up to the lower thermosphere and cause a lot of large perturbations, and the implication of which still need to be further determined, especially for the ionosphere. So maybe I'll skip this. So this is animation. Thanks for those who showed this last 2 days. And so what I showed here, this is the same animation showed by my colleagues in the last 2 days. And this is from the same same simulation, WACOM simulation, but also for Meridional wind, but at the surface. So you can the main point here is try to see to show the very different dynamical scales, both temporal and spatial scales in the lower atmosphere and upper atmosphere, and also to demonstrate that it's very important to consider mesoscale dynamics up in the upper atmosphere. And I just point out to compare the regular resolution and high resolution model. First of all, we're extending 2 decades now for good, to resolve things reasonably well before we have a sharp drop in the spectrum. And also for the regular res, we can see that it can resolve things pretty well up to wave number 10. So if you want to study anything with a finer scale, we're not doing very good job there. So the mesoscale resolving is really critical there. And to demonstrate that, this is what we got from the high resolution model, the wind shear profile from the ground to the lower thermosphere. And this has been always observed, but cannot be reproduced in our previous models. And now with the high resolution model, we have a much larger dynamical range, and we can really produce this kind of large shear and wind zone in the lower thermosphere. And we compare that with the wave intensity with observations, and seems they're in good, reasonable agreement. And this is a recent study by George Colodis from NOAA and his students. And they took the model results and did some spectral analysis for the lower atmosphere. So this is really looking at the source region to see how well we're doing or how bad we're doing using the high-res model. And this is the symmetric mode and anti-symmetric mode from the precipitation. This is compared with the trim. Even though this is a little bit spotty because the duration of the simulation is still short, but we are capturing a lot of the Kelvin waves and the Rossby waves modes in the observation, and even a little bit of signal in the Maiden-Julian oscillation. And this is a wind a bit higher up at 50 hectopascal, and also seems to doing pretty well in high res. So I'll skip that, and just a summary. We are consider a lot of things, and especially the 4 aspects: the regional coupling, lower and upper atmosphere coupling, the ion-neutral coupling, and cross-scale coupling, and using the high-res model. And also using the model, we can study the upper atmosphere predictability and also develop data assimilation capability. And these are some of the future development. And as I mentioned earlier, NRL, our colleagues at NRL is developing a coupling with the plasma sphere model, the SEM03. And the data assimilation, we like to push further to assimilate ionosphere and thermosphere data. And some maybe interesting projects in the future to further look at the mesoscale model, what can it do and what can it reveal about the lower or the upper atmosphere. And also, all I talked about is mainly concerns the upward coupling. And recently, we got some fund to work with our solar colleagues, Matthias Rampel, to look at maybe the solar impact, the downward coupling and the solar impact on the climate. So we're very excited about that. And also, I think this is a big question we would like to delve into. And I think it's not just for upper atmosphere. The multi-scale dynamics is a very general question we would like to study using the new model capability. Of course, it's a teamwork, and we have an HAO team, and we're very excited that the real future generation scientists will come here, and the ad is already out, and collaboration with ACOM, CGD, IMAGE, and COSMIC. Thank you.
And while our next speaker sets up, any quick questions for Hanley? WACOM and WACOM-X are really a true kind of cross-NCAR collaboration and offer pretty exciting insights into the upper atmospheric system and the up-down coupling. Any questions for Hanley? You can have a comment, absolutely.
I can say spectral polarimetry. Anyway, Hanley?
Yes.
Hanley, I was just going to comment, it was really exciting to see all the different models being used, and then the analysis on trying to see how they differ and why they differ. I think that was just really exciting to see everybody coming together on that. Very exciting. Thank you.
Thanks again, Hanley.